In this video, we will try to derive a geometric interpretation of Newton's method that we have seen in the previous video. In the context of equations, the interpretation of Newton's method is that at each iteration, a local linear model of the function is calculated and is solved at each iteration. In the case of optimization, where we try to make the gradient is equal to 0, we will see that the model that is calculated by the algorithm at each iteration happens to be a quadratic model of the objective function. This is what we will illustrate in this video. So here the objective function that we try to minimize is a function of n variable, and we assume it's twice differentiable. Then at each iteration of the algorithm, it calculates a model around the current iterate that I denote by x hat in this equation, which is calculated based on the Taylor's expansion of the function around x hat. Combines the value of the function at x hat with the value of its first and second derivatives to get a polynomial approximation of the function given by this formula. And this happens to be a quadratic model. So let's take this function of one variable, which is actually a polynomial of order 4, which is plotted on this picture. And now let's consider this point, xk equals 2.5. Let's apply Newton's method, and to do so, we must calculate the quadratic model that approximates the function at xk equals 2.5. This is the quadratic model, it's a parabola. And the idea of Newton's method is that to consider the parabola, and instead of minimizing the nonlinear function, minimize the parabola instead, find the minimum of the parabola. And this happens to be this point here, which is the minimum of the parabola. So this point becomes the new iterate. In this case, it's 3.636. And then Newton's method starts again. It calculates a new quadratic model of the function at that point and minimizes this quadratic model. And you see that in 2 iterations, we are very close to the local minimum of the function. So again, we see here the fast speed of Newton's method in terms of convergence. And in this example, we happen to converge to a local minimum very quickly. Okay, so if we zoom, we see that after 2 iterations, we are very close to a local minimum. And we actually see as well that the model that we have calculated, the quadratic model that we have calculated, is actually very close to the function, close to this point. So it's a good approximation of the function. But let's try the same method using a different example. So instead of starting our algorithm from 2.5 as before, let's start the algorithm from xk equals 4. And let's apply the same algorithm. So if we calculate the quadratic model, again, it's a parabola. But if we calculate the minimum of this parabola, this point here, we obtain for the objective function a point which is higher than the previous point. So it means that in this case, an iteration of Newton's method generates a point, an iterate, which is worse in terms of the objective function than the previous one. And intuitively, we can understand why, because the quadratic model that we have calculated happens to be quite good around the iterate xk equals 4. And this is actually guaranteed by Taylor's theorem, is that it is a good approximation in a neighborhood of the point where it's calculated. So the quadratic model is good around xk equals 4. When you look at the minimum of the parabola, which is something like xk equals 2, well, in this area, the function and the model do not match. So the model is a very poor approximation of the function at that point. And in this case, the method will not work because it generates points which are worse than the previous one. Let's take another example. Xk equals 5 now. Now, if I calculate the quadratic model at that point, what we obtain is a concave parabola. So 2 things may happen. So if I want to solve the system of equations, so to find the value of x such that the gradient is equal to 0, what I will obtain is the maximum of the parabola. And if instead I try to minimize the parabola, well, it's unbounded, so there is no solution. The parabola is not bounded from below. So we are in a case where the function at the current iterate xk equals 5 happens to be concave. And because the function is concave, well, the parabola, the quadratic model that we calculate, is also concave and therefore unbounded. So in this case, the method does not make sense, because either we try to solve an unbounded minimization problem, or we calculate a maximum, which is not what we want to do. So we have seen 3 cases in this example. One where the method works well, it converges fast towards the local minimum. One case where we find a convex quadratic model, but that does not match at all the function around the optimum of this model, and therefore it may generate points which are worse for the objective function. And the last example we saw is a case where the function is concave at the current iterate, so that the quadratic model is concave and cannot be minimized. So these are the issues that we will have to fix in order to make the Newton's method useful for optimization. So let's provide a couple of definitions before we proceed. We call Newton's points the following point. So we have a function f with n variables and a real value, which is twice differentiable. And we have a current iterate xk. And here we insist that the second derivative matrix is positive definite. So it means that at xk, the function must be convex. So what we call the Newton's point is a point that basically represents the next iterate of Newton's method starting from xk. So it's xk plus the direction dn, and dn verifies what we call Newton's equations, which is given by the Hessian of f times dn, which is equal to minus the gradient. This is the definition of Newton's point. So it's the point which is obtained by applying one iteration of local Newton's method to a current iterate xk. Before we conclude the video, let's define another point that we will see useful later on. We call it the Cauchy point. So again, we consider f to be twice differentiable, and then we have a current iterate, and we also would like the function to be convex, but we just need to be convex in the direction of the gradient. So in this case, the Cauchy point of the function at xk is given by moving away from xk in the direction of minus the gradient and doing a step called alpha c in this direction. And alpha c is calculated as the inner product of the gradient of f by itself divided by the curvature of the function in the direction of the gradient. So this point is called the Cauchy's point. Basically, it is interpreted as the minimum of the quadratic model in the direction minus the gradient, and is calculated using these equations. So we have seen in this video that the interpretation of Newton's method to solve optimization problem is based on the calculation of a quadratic model at each iteration. We calculate the minimum of the quadratic model, and this minimum becomes the next iterate for the algorithm. But we have identified 2 problems associated with this. The first problem is that at the minimum, the quadratic model may be a poor approximation of the objective function, and in this case, it may generate iterates which are worse than the previous one. The second problem is that if the function is not convex at the current iterate, the quadratic model that we generate may be unbounded, and therefore we cannot minimize it. It shows that we will need to make some adaptation to this method before it works for solving optimization problem.